I have much less information that is reliable to discuss the possibility of intelligent civilizations out there. So please bear with me. The other thing is, I wanted to emphasize that this is a bit of a speculative discussion. Nobody is suggesting here that somehow we're proposing an answer tonight. It's more like we should, I'm trying to possibly raise some questions on a topic that is very old, but at the same time has the benefit of getting a little bit of new information, especially now. So the title is Home Alone, Why Microbial Worlds Might Be Common, emphasis on might, but intelligent civilizations might be exceedingly rare. Okay. So this is the Andromeda Galaxy. It's a swarm of stars, just like the one that we ourselves are embedded in, the Milky Way galaxy. It's a large galaxy. This one is one of the closest large galaxies to us. It's located 2 million light years away. Okay? I'll get to the exciting part in a bit. Okay. Andromeda has approximately 100 billion stars. Okay? And our own galaxy, if we were able to sort of step back and look at it, might look something like that. It has spiral arms. It's sort of a nicely flattened disk. Again, we are approximately of the same size, so about 100 billion stars is what surrounds us. That's a 1 followed by 11 zeros. Okay? That's a large number. And we're not even, of course, in a central position by any means. We are off on some arm off of the center of the galaxy, of our galaxy. And our star is not a particularly exciting star. In fact, it's almost the personification of the run-of-the-mill medium-sized star. There's nothing about our position around our star that is particularly remarkable either, other than we happen to be in a zone where temperatures are not too hot for water to remain liquid or too cold for water to remain liquid. Okay, so to the extent that you're interested in liquid water, we are in a good place. But I'm jumping ahead. What I wanted to say, though, is that as a premise, I grew up with the sense that if you were to be open-minded, you sort of had to imagine that our galaxy would have other civilizations. In fact, if you were somehow assuming that we would be alone, you would be a bit presumptuous or think that somehow we were the result of some divine intervention. But if you felt that we were actually part of a process that's a natural process and could be repeated elsewhere, your natural inclination as an open-minded person would be to assume that we're not alone, and that in fact there must be bars out there where we could hang out with interesting peoples. And in fact, this is really pervasive in our popular culture. Star Trek and Star Wars are sort of the epitome of science fiction or fantasy, and they both portray a galaxy that's populated by lots of alien civilizations. Okay? So the question is this really the type of galaxy we are in? So there's actually a mathematical formula to give you the number of alien civilizations in our galaxy today. And by intelligent civilization, we mean a civilization that's capable of radio communications. It doesn't mean that they're actually communicating with us, but they're capable of it. It assumes some stage of understanding of the laws of physics. We assume that they're the same for everybody, and that they can somehow use radio waves to communicate if they chose to. This number is expressed by this equation, but it's really just a formula, and it's mathematically very simple. It's multiplication of 7 terms. And the idea behind this Drake equation, which was proposed by Frank Drake back in the late 60s, is that if you actually knew the exact value of these 7 terms, you would actually get a number that's pretty close to the actual number of alien civilizations in our galaxy right now. Okay? Of course, the catch is we don't know the value of several of these numbers. Okay? So while it is mathematically robust, it's actually not very well defined in terms of its parameters. Now, On top of that, there are some complications that could be reasonably real in real life that are not reflected in this equation. So in some sense, it's a simplification of things. But what this does is that it then gives you a lower estimate of the number of civilizations out there. Because if you had a civilization, for example, that was actually colonizing the rest of the galaxy and essentially implanting itself as life on more than its planet of origin, an equation like that, as a simple linear equation, would not reflect that properly. But at least we have something that gives us a starting point. So this is how it works. The number of alien civilizations in our galaxy right now is given by the average rate of star formation in our galaxy, times the fraction of those stars that actually have a planetary system around them, times the number of environments within each planetary system that is actually suitable for life. And it doesn't mean that there is life, it's just suitable. And by that we mean it has liquid water in abundance and for the duration. This is definitely a bias towards what we like on Earth, but it's a starting point. Times the fraction of those environments on which life actually emerges, times the fraction of those planets or environments where life actually emerges that actually become intelligent, and we'll define that down the road, times the fraction of these intelligences that become an actual civilization, and by that we mean radio communicating, times finally the average longevity, so that's a number in years, of a civilization. The assumption here being that they don't last forever, nothing really does. Now, the rate of star formation in this context, you can understand that it's sort of a number of stars per year, and it's there because it represents the creation of opportunities for life to then sort of develop from planets that would be around these stars. Okay? So that's how this equation goes. So classically, there have been optimistic estimates. These are all numbers, okay? Optimistic estimates and pessimistic ones. Let's get the pessimistic ones out of the way. If you gave very small numbers to any one of these terms almost, and some people think that they're very small, like for example, some people think that chances, the fraction of planets where even if the environment is good for life, where life actually emerges, F sub L, is actually a very small number, much less than 1, that's what it means. Well then, the total number in the end is much less than 1. So we should not even be here according to these pessimistic estimates. On the optimistic side, it sort of gets interesting because, in fact, if you look at a high rate of star formation on the higher end of things and allow the other numbers to be basically at 1, meaning 100%, then if you're sort of optimistic about the average longevity of an alien civilization and giving it, say, 1 million years, okay? Why 1 million? Well, because it's a nice big number, okay? You end up with a number that's about 50 million civilizations in our galaxy right now. Now, that seems like a big number, but bear in mind that there are 100 billion stars. So this means that there would be an alien civilization like us, well, in terms of our capability or more capable, 1 every 2,000 stars. Okay. So on average, the nearest alien civilization to us would be about 80 light years away. All right, so now that's interesting because we've been radio loud since about 1933. And that's because Hitler in Germany was making very loud broadcasts of his speeches. And in fact, if you were to sort of listen to the Earth throughout history, the first wave of radio bursts coming out of the Earth would be Hitler's speeches. This is quite a way to give a first impression of people on Earth. And interestingly, 1933 plus 80, okay, is 2013. So just this year, if there actually were an alien civilization 80 light years away, in the optimistic scenario here, they would be getting Hitler's speeches as we speak. Okay? So they're hopping onto their warp drives, they're on their way. All right. So the talk today is to sort of put some rhyme and reason maybe behind some of these numbers and see what really is a more plausible outcome. There's something called the Fermi paradox that you should also bear in mind. Enrico Fermi won the Nobel Prize. He was a great physicist. He was born in Italy. He immigrated before the war. He joined the Manhattan Project in Oak Ridge in Tennessee. And he actually was an incredible guy in the sense that he was not only a very good theoretical physicist, but he was also a very good practical experimental physicist. Okay? And as a practical person, his point about this issue of alien civilizations is, if there are so many of them, if n is actually a large number, where are they? Okay, where's everybody? Shouldn't we be hearing them? Shouldn't they have come here? Shouldn't they be here? All right. And so that was a good point. And there have been, over the years, a number of excuses for Fermi's paradox. In other words, they are there. There are many of them, except that, okay, so let's go through this a little bit. Interstellar communications and travel are just too difficult, so most of them don't find that it's worth pursuing. Okay, so, but they're out there, they're not bothering with it. Intelligent civilizations are too alien. So in other words, they're communicating, but we're just not getting it. We're not understanding what they're saying, and we're not even realizing that they are. It's lost in translation is how I interpret that. Intelligent civilizations are too advanced or busy. Okay, so in other words, we mean nothing to them. They have other fish to fry, and we should perhaps lay low, really. Intelligent civilizations are not radio loud for long. Now that's an interesting one. We have been radio loud for quite a while, since the 1930s, but it could be that past a certain point, our technology would rather revert to things like optical communications, things that are no longer really requiring radio communications in big, powerful bursts. And so there could be a spike in our radio loudness throughout our longevity. Okay, so we're sort of loud when we're young, and then we sort of become quiet. So essentially, this would mean that they are out there. We don't hear them because they've all switched to cable. And that actually is a possibility in reality. Okay? Intelligent civilizations are avoiding us. So Carl Sagan used to say that that's the best proof that they are intelligent, because we dumb and loud. Okay? Intelligent civilizations are breeding us. So this is the idea that we are somebody's ant colony. Okay. They are protecting us. So this is because they know about the Prime Directive. They watch Star Trek II, and we are being protected. They are studying us. This is telling us that we're somebody else's science project. They are training us, okay? And we just haven't been deemed worthy enough to join the community of galactic civilizations. We're not potty trained yet, is sort of the idea. Intelligent civilizations can't agree on what to do. Should we communicate with these people? Should we send our vessels there or not? Okay, that's the theory that, well, they might have a Congress as well. Okay, so no decision is made. Intelligent civilizations are here, but they are unseen. So we're in a lot of more trouble than we think, okay? Is this possible? Well, you know, Arthur C. Clarke used to say that past a certain point, technology is not distinguishable from magic. So they could be just far enough ahead of us that they could be amongst us and we wouldn't even know. I don't think that's true, but that's an argument that's being proposed. Others are that the SETI effort, the search for extraterrestrial intelligence, is sort of a young effort. We've only started to listen to stars where we haven't scanned the whole sky. And so we can't really conclude yet. SETI is misguided. We're not doing it right. So they are out there, they're being loud, we should be able to detect them, we're just not listening maybe at the right frequency or something. And then there's also the notion that they have come, we are in communication with them, we're just suppressing the evidence, especially at the SETI Institute. So I cannot comment more on this. What it says there is, this space left intentionally blank. Okay, so let's go back to the Drake equation and realize that, in fact, what's really nice about it is that to get a number behind any one of these terms, you actually need to call upon very different fields in science. And in fact, the SETI Institute is sort of an interesting organization in that sense. When you get hired as a scientist there, you could be a sociologist, in which case you're hired to address L. You could be an extrasolar planet person, in which case you're hired to address F sub P. Okay, so you are sort of, you fit somewhere in this whole thing. Frank Drake himself used to say that this equation was a way of organizing our ignorance. Okay, and I sort of like that very much because it's humble, and at the same time it really is a description of this thing. So astrophysics is involved for R sub-star, meteoritics, extrasolar planets. You can see the various fields of study that are involved. So what do we know about these numbers today? Okay, so the rate of star formation is determined by studying regions in our galaxy where we see stars forming actually today. So we see these beautiful areas that have been imaged by Hubble in particular, where we see these stellar nurseries with groups of stars forming as clouds of gas and dust collapse and start slowly spinning. Usually stars are not formed one at a time, but in groups. And here are different views of these nebulae, these cloudy formations out there across the galaxy where stars are being born. And so you can figure out how many there are of these and how many on average stars are produced in each and one of them, and then come up with a number that will represent the average rate of star formation in our galaxy. Okay, so I think these are all incredible images from Hubble. And the number is actually relatively well constrained. It's about 20 to 50 stars per year. Okay? So it's not 1,000, nor is it 0. So I'm going to be somewhat conservative on this one, but not really far from the maximum anyway. R sub star, about 20. Okay? All right. What fraction of these stars has planets? Well, we actually know relatively well how planets form, in the sense that we've had models for their formation for quite a while, and they seem to be more or less holding up. It involves the collapse of disks of, again, dust and gas. They start spinning, angular momentum is conserved, and meanwhile they heat up. First of all, because there's a central star, but second, the collapse itself is producing quite a bit of heat. And so the particles in this cloud are, in some cases, even melted. But first, they do start colliding with each other as the flattened disk is more dense in particles. The particles start clumping together. It's a process called accretion. Next thing you know, little planetary bodies or embryos are formed. They're called planetesimals. Planetesimals run into each other. Sometimes they just explode. Okay, they just break up again, and you sort of start from square one. But in other cases, they keep growing and growing and growing, and next thing you know, a planet is on its way. So this is how we think the planets in the solar system formed, more or less. And this is how we think planets around other stars are formed as well. We actually have some data, some tangible data about the conditions that led to the formation of planets in our own solar system. This is a section from a primitive meteorite. There are meteorites that are not primitive. There are meteorites that are still very pristine. This is a very pristine one. Each one of these little globules is about 100 microns across, okay, so 1/10 of a millimeter. And they are called chondrules. They are little spheres of silicate, so essentially rocky material, that have been turned into spheres because their outer portion seems to have been melted from the high temperatures in the disk of gas and dust that was spinning up and forming the planets at the time of planet formation. Okay, so we have a handle on what was going on. These things are also rich in carbon. That accounts for the black matrix that's binding these little particles together. And if you notice also, there's this odd-shaped bleb in there. That's actually a bleb made of calcium and aluminum and other high-temperature metals and elements. This is actually telling you that our planetary system is not a first-generation system. Okay, so in other words, when the planets formed in our solar system, it did not form from the collapse of an original cloud of mostly hydrogen and dust, like most primitive planetary systems are formed. We are forming in a pretty dirty cloud. Out of a dirty cloud, which had the debris of stars that lived before us. Okay, so these metal blebs are the direct proof that other stars lived their lives before our own sun formed. They died in catastrophic explosions, in supernovae. These events created these heavy metals, which then got incorporated in a subsequent collapse of a cloud of gas and dust that formed our planet. Okay, so we are not made out of fresh stuff. But anyway, the process still remains roughly the same. And then, of course, now we actually are in a golden age of the discovery of nearby planets around nearby stars. And one particular mission called the Kepler spacecraft is focusing on this part of our galaxy. So just this cone that you see that's highlighted here, all the way out to about 3,000 light years. And it's checking out the various stars in this branch called the Orion spur of our galaxy, and looking for planets around the stars in this particular location. And this is how it works. It captures the light coming from the star, and if you're lucky enough that the plane of the system is sort of along your line of sight and crosses the disk of the star, once a planet comes by, you will see actually a dip in the light coming from that star. So if you can imagine the sensitivity of Kepler, it's quite incredible. It's able to see the passage of a tiny little dot and detect the drop in the light coming from the star just from this transit, okay, from this transient event. So as the planets go round and round the star, they will essentially eclipse part of that star for a little while, and you can see that the light from the star dips a little bit and then goes back up once the planet exits. So it's doing this for lots of stars, and as of last night, the number of confirmed planets from Kepler is 156, okay, planets around nearby stars in that cone. And the number of candidate planets that are still being sort of monitored, because you don't do this just once, and of course some of them are traveling very slowly around their star. It takes a while to confirm a planet. There's about 3,500 that are candidates that are waiting for confirmation. Okay? So we're really in a golden age where the number of exoplanets, planets around nearby stars, is exploding. So what's this number? Well, strictly speaking, since we're only looking at a very narrow part of the sky for now and have not really checked out every star possible, we're also focusing on a particular type of star, these categories of stars that are more or less like the sun. We're also tending to detect larger planetary bodies rather than the smaller ones, although some smaller ones are showing up now. The fraction of stars that actually have planets could be anywhere from 5%, but not lower than that, all the way to possibly all of them. Now, is it reasonable that all of them would have planets? Probably not. But what seems to be showing up here based on these surveys at this initial stage is that a substantial fraction of stars actually have planets. There's a terrific article that's in the November issue of Scientific American that talks about planetary systems around double stars, binary star systems. Okay, binary star systems were believed in the past to not be very stable places for there to be planets around them. So you have two stars going in orbit around their center of mass, and then meanwhile, how could this complex system still allow planets to be going either around one of the two stars or both at some farther distance out? Okay. Well, that's all explained, and these are marvelous planets. Imagine us, having two suns. Okay, it's just like in Star Wars on Tatooine, they have that. Okay, but the sense here is that planets are no longer rare. We know this. It's not a number that's close to zero. It's a number that is large. It could be 50%, and at this stage, it could be anywhere from 0.3 to maybe 0.7. Okay, so 0.5 is sort of a reasonable estimate. I wouldn't put it at 1 just because we don't think that every star will have planets. So once you have planets, how many environments within the planetary system will be suitable for life? How many will have water? So there's this notion, first of all, of a habitable zone around a star. First of all, you have on the vertical axis stars of different sizes. Okay? The sun being, in this case, shown as the largest star that we're considering, but of course there are much more massive stars above the sun. And then on the horizontal axis, you have different star systems that have been discovered or characterized to date. Okay, so if you just focus on the line that corresponds to our sun, where we have a yellow star there with a mass of 1 solar mass, you can see that Mercury is at that relative distance from the sun, and there's Venus, Earth, Mars, and then farther out, Jupiter and Saturn. Okay, so that's our solar system. What this diagram shows you is the zone, the distance from that star to the left of it, where the temperatures are sort of suitable for liquid water to be present. So quite obviously, if the star is relatively big, in this case like our sun, okay, the zone is going to be farther out, okay, because the star is emitting more light, more energy. Okay, so if you're too close, you're going to be too hot. So, but meanwhile, if you go to dimmer stars, this habitable zone will just get closer into the dimmer star. So the distance at which you will find a habitable planet from the standpoint of liquid water being stable, okay, is going to be different depending on the size of the star that you're looking at. Right? Well, in our solar system, both Earth and Mars are supposed to be in a pleasant habitable zone. Okay? We're finding star systems that are around smaller sized stars that also have planets that seem to be in their habitable zones. Okay? So we're slowly making our way here in mapping these planetary systems and are making some incredible findings. Notice that a lot of these planets that we're finding in habitable zones are relatively large. They're called super-Earths. That is really a reflection of our limit of detection so far. We tend to be finding planets that are somewhat bigger than our own. But as we refine our search techniques, we're going to nail smaller and smaller size planets. And in fact, Kepler has recently discovered a planet that was about the size of our moon. All right, so we're getting there. But let's see if Mars really qualifies as a planet where you would say that things are habitable. So this is planet Mars, and I'm not going to go into a lot of detail here, but for all intents and purposes, it really is, by Earth standards, a cold planet. Okay, there's no liquid water at the surface, not clean water at least. There might be some brines, water with a lot of perchlorates and other nasty salts in them that could keep the water liquid if the salts are dissolved in the water. But generally speaking, it's a desert on a global scale, and it's a cold one at that. The average temperature on Mars is minus 60 degrees C. Okay. We've landed in 7 locations on Mars. They were all US successes, I have to say that. 1976, Viking Lander 1, all right. Sand, a few rocks. Viking Lander 2, rocks, a bit of sand. Mars Pathfinder was a fixed lander, but it carried a little robot rover the size of a skateboard. You can see it. It's over there. It was called Sojourner. It's next to that big rock. Okay, rocks, a bit of sand. Interestingly, Mars Pathfinder died. It was sort of the mother craft. It sort of lost power and died. But Sojourner, for all we know, was programmed to keep on going. And it had little solar panels of its own. It was nicely powered. And it was programmed to run into a rock, back off, turn, keep going. Run into a rock, back off, turn, keep going. So for all we know, it's roaming around on Mars somewhere, even now. Unlikely, but. Phoenix. Phoenix was a fixed lander. It landed near the North Pole of Mars. The idea here was to check the hypothesis, or at least even the orbital observation, that at high latitudes on Mars, there was a lot of ice in the ground in the top meter or so. Okay, and sure enough, it lands here. It doesn't see ice right now, but it scratches the dust off of the surface, and it exposes bright white ice. Okay, so it's massive ice that is right there underneath the dust, the diffusive barrier that the dust forms above the ice. Okay, so it's not really news because we were expecting that, but it's nice to see it confirmed. Mars is a H2O-rich planet. There's plenty of ice. There's ice in the North Pole. At the North and South Pole, there's ice in the atmosphere. There's ice in the ground massively at high latitudes, both north and south. There's just not a lot of it that's liquid, okay, of this H2O. Spirit landed in this place, mostly a flat rocky plain, but it was on the inside of a large impact crater. Opportunity landed outside of several large craters, but has been exploring them from sort of the plateau around them. Opportunity is still working. And then this is one of my favorite shots. It's a location called Yellowknife Bay inside Gale Crater. It's named after Yellowknife, yes, in your Northwest Territories. And it's just a piece of desolate corner of Mars, but it's very beautiful. And the story is, however, the same. Okay, no liquid water, not only that, but no organics. Okay, so this is really now a recurring theme. Martian surface seems to be really hostile to the preservation of organic material. And we're not even necessarily talking about biological organics. Things like even methane are not found on Mars. Even though there's plenty of carbon and oxygen in the atmosphere in the form of carbon dioxide, we are not seeing any organic material inside rocks, even when you scrape through the rust on the crusty outer shell of rocks and go to the inside. Okay? So it's an environment, therefore, that's cold, dry, and poor in organic material, key things that life as we know it would like to have. Okay? So as much as I find exploring the surface of Mars exciting, I think we need to sort of maybe reach for a third dimension now as we move forward and go into the interior. Now, there is no doubt, in fact, it would have to be really odd that there would be no liquid water deeper down on Mars where it's warmer. Okay? There is the amount of ice that's in the northern and southern hemisphere underneath the surface is so massive that at some point beneath that permafrost, you have to encounter a horizon where the temperature is going to be high enough for water to be liquid. Okay? On Earth, everywhere where you find water, liquid water, there is life if the water's clean. And every form of life that we know of on Earth needs liquid water, even in the desert. It doesn't need liquid water all the time, but it needs it at least sometime. And so this is why finding liquid water is such a key thing to conducting a plausible search for modern extant life on Mars. Okay? Fossils, you can look for them at the surface, but life that is really still alive today, you got to get to the liquid water. So if you drill anywhere on average Mars, it could be a while till you hit the liquid water horizon, 1 to 2 kilometers. It would help if you start at the bottom of canyons. So I think a first human mission to Mars could go to the floor of Valles Marineris, because the liquid water will be about 1 or 2 kilometers shallower than elsewhere. But another good place to look are the volcanic regions, okay? Because there, the temperature gradient, the rate at which the temperature increases as you go underneath the ground, okay, will be steeper. To the extent that these volcanic regions are still active, you might actually have a better chance of finding liquid water at shallower depth if you go to these volcanic regions. This is the largest volcano on Mars. It's the tallest mountain in the solar system. The profile at the bottom shows you Olympus Mons compared to Mount Everest. Okay, so if you've climbed Mount Everest, remain humble. Okay, Olympus Mons is 3 scale heights above the Martian atmosphere. Okay, so it's well above the Martian atmosphere. If you're standing at the top of Olympus Mons, the sky is a deep purple or black. You're essentially standing in space. Okay, you can close your eyes and you'll see flashes. That's cosmic rays hitting your retina. It's time to head down. Okay, but we see lava tubes on the flanks of the volcano. Those of you who might be into volcanology, we see entrances of lava tubes, okay, collapsed lava tubes, windows into the flanks of the volcano. All right. Beyond that, there are other environments that expand this notion of habitable zone. Habitable zone is defined as the distance from your main star, but you know what? Even in our solar system, we actually have environments where liquid water is present for the duration, and they are not technically in what you would consider the Goldilocks zone around your star. And so this is really important because we're realizing now that the upper atmosphere of Jupiter has water clouds, among other things, and so could be an environment where there might be creatures. The moons of Jupiter as well, we see Europa here, could also be a good place to look. So let's check this out. This is going back to Cosmos and ideas by Edwin Salpeter at Cornell with Carl Sagan. They speculated in a historic paper that the upper atmosphere of Jupiter might be home to an ecology. All right? So you had floaters that would rise with the thermals in the atmosphere of Jupiter and collect food on their way up, and then they would sort of cool down. They had a bit like jellyfish, the structure of a balloon, and as they cool down, they would sink because it would be denser, go back down into the warmer parts of the upper atmosphere, and then rise up again. All right? Speculation, of course, but it's interesting that from a thermodynamic standpoint, you actually could have at least microbes from Earth living in that kind of environment. Jupiter is replete with nasty radiation, but where you would be sort of not completely at the surface of the planet, but deeper down in its upper atmosphere, you would be shielded from the bulk of that radiation. Okay. Europa is one of the 4 large moons of Jupiter. It has a crust of ice. Beneath this crust, there's an ocean of liquid water. We think it would account for this Arctic sea ice morphology of the surface. So this is what this thick crust of Europa would look like. It's a really thick crust. It's 1 to 2 kilometers thick at least. And of course, we're not thinking, although that has been proposed, of setting something underneath the crust. We're more looking at how we might land on one of the cracks, okay, and look at what's coming up through the cracks or has come up in the past through the cracks. Another moon of Jupiter, Ganymede, it's farther out. It's bigger. It's in fact the largest moon in the solar system. Ganymede is even larger than Mercury, all right? It has a thick crust of ice, but deeper down a slushy mantle made of liquid water. And it could have, well, it has some liquid water. And that also is an environment where you could conceivably have subsurface microbes like we find deep down on the Earth as well. And then one of the most exciting possibilities is Enceladus. Enceladus is one of the moons, icy moons of Saturn. It too looks like the Canadian Arctic. And along these cracks, we actually are seeing, now this is imaged by Cassini, okay, a spacecraft in orbit around Saturn. We're seeing geysers, essentially, or sprays of water and water vapor, ice crystals, or water vapor, and it turns to ice crystals, coming out of these cracks and holes in the crust of Enceladus, all right? So what's generating all this heat are tidal forces that are in the Saturn system, just the same thing as Europa. But you can see that how this is a very dynamic place, and so you don't have to go into the ocean underneath the ice crust to look for possible life. You just have to land in the right place to look for fresh fountain deposit. All right, so going back to the number of environments that are suitable for life in the solar system, it's not one. Okay, as far as finding liquid water that's stable on geological timescales, millions of years, we have at least 6 environments in our own solar system, possibly 7 or 8, depending on whether Callisto, another moon of Jupiter, and a few other places have liquid water deep down. So all of a sudden, this has been really a discovery of possible habitats in our own solar system and the result of the space age. Okay. So this number n sub e could be anywhere from a relatively small number in case there are planetary systems that are somehow really not offering an opportunity to be in a habitable zone or offering large bodies that have subsurface rich in water, etc., to be, all the way up to possibly 10. And again, number 10 is an astronomer's approximation of 7 in the case of our solar system, 6 or 7. Okay. So I'm going to submit to you that since we don't know what n sub e is, let's call it 1. It's neither a very large number or a very small one. What this is saying basically is that if you have a planetary system around a star, the average number of environments where you find liquid water stable for millions to possibly billions of years is probably one system within that planetary system, okay, one planet. Now, that's optimistic. And I want you to remember that it's optimistic because in spite of how optimistic we are, you'll see the result at the end. So we have liquid water. Does life automatically emerge? So this is one of the earliest forms of life on Earth, a bacterium, okay, a cyanobacteria. And one of the things that is quite remarkable is that life on Earth appeared very early. Okay, and that's the most remarkable thing to convey about that. This is a column that shows you the entire history of the Earth. At the bottom, 4.6 billion years ago. At the very top, well, not quite where it says you are here, all right, that's the present. That's 4.6 billion years. The entire red column is life that has been mostly microbial only. Okay? Not quite, it's been growing up a bit in size towards the Cambrian, but very simple organisms throughout the bulk of Earth's history. Okay. The oldest rocks we have a record of on the Earth are 4,000 years old, and the earliest signs of life in ancient rocks are found in rocks that are about 3.9. Okay. What this tells us is that the process that allowed life to take hold on the Earth, okay, was very rapid. So I take that to mean that the fraction of planets where the environment is right for life will be high, that they actually have life emerging on them. Okay, and this is, again, only taken from the one example that we have, the case of life on Earth. It could be completely off, but if the Earth is representative of a general rule, then F sub L should be a number that's close to 1. It's not exactly 1, just to be a bit conservative, but we're giving it here a number of 50%. Now, I want to point out that there are some incredible weird things here in the record of life on Earth. This is a single cell called Deinococcus radiodurans. Okay, it's a microbe, it's a bacterium, but it has compartments inside, and it's a radiation-resistant microbe. Not only that, but it's resistant to vacuum, it's resistant to high pressure, it's resistant to cold. It doesn't like high temperatures, although there are some versions of it that do. And it doesn't mind being dry and away from water for a long, long time. Okay? Not only that, but it's radiation resistant because, as a real weird thing, it has 4 sets of DNA. And you see the DNA there. Okay? Its DNA is in 4 sets, each isolated in little compartments. If this thing gets zapped by a cosmic ray or some radiation particle that destroys the DNA in one compartment, the others race to the rescue and restore the information from the backups and the backups and the backups. Okay, it's really remarkable. And in fact, it's so remarkable that there have been papers written about, speculative papers, that this is sort of an alien bug. It's designed for space travel. Okay, and whether it actually came from space and somehow it's just in our ecology, or whether we are actually descendants of something like that. And so that's why life started so quickly. It's because it didn't really have to start on Earth. It just came to Earth once the Earth was able to accept life. So this is very speculative, of course, but it's a remarkable family of microbes, these Deinococcus radiodurans. And if you're into biology, I would recommend you study these. What fraction of life then turns into intelligence? Well, this is who we define as intelligent in our case. This is Homo erectus, showed up about 1 million years ago, started to control and be able to make fire, built things, of course chisel at rocks, but was a remarkable being and essentially really close to being on its way to being us. Homo erectus, of course, started in East Africa, but was found very quickly over the following few tens to hundreds of thousands of years in Europe, including in Britain, in Indonesia, and on its way to Australia. So this is an early form of Homo erectus, okay, in Eastern Africa. And so this is what we mean by an intelligent society. Okay, a society that is starting to be able to change its environment through technology, but is still not doing radio communications. Well, Homo erectus showed up just 1 million years ago, okay? And in the big column of things, it really is at the tail end of the history of the Earth so far. If you were to visit the Earth randomly throughout its history, okay, there are only 2 chances in 10,000 that you would find something like Homo erectus or closer to us. Okay? 2 chances in 10,000. So we have really been occupying the very final stages of the evolution of life on Earth so far. And for the bulk of the history of life on Earth, we haven't been around. So this is suggesting that F sub I is actually a small number. Okay? In other words, it's very difficult for life to go from microbes, including radiodurants, to something like us that's capable of technology. And so how do you quantify that? It's difficult. My suggestion here is that we simply make it the ratio for how long we've been around as Homo erectus or better versus the age of the Earth. That's 1 million years over 4.6 billion years. The fraction of planets where there is life and where this life actually evolves into intelligence would be about 2 10,000ths. Okay? The real number could be even smaller, but we might not have time to discuss it. From then on, what fraction becomes a civilization, an intelligent civilization? Well, that's between Homo erectus and getting to this point where you build radio telescopes and you, by definition, understand Maxwell's equations. So, according to SETI, you're not civilized. You are intelligent, but you're not civilized unless you understand Maxwell's equations. So, intelligent life to the left, intelligent civilization to the right. Okay? This is the same guy that you saw earlier. Okay? He just had a hair club makeover. But Homo erectus to James Clerk Maxwell, who came up with Maxwell's equations, that took about 1 million years, all right? So that seems to have been, sort of geologically speaking, a straightforward process which could suggest that becoming a civilization, once you're intelligent, could be F sub c equals 1. But the thing is, you could imagine some dead ends to intelligence. You could imagine a society that actually becomes as smart as Homo erectus, but somehow is in an environment that doesn't require it or doesn't drive it to inventing mathematics or Maxwell's equation or builds telescopes. Okay, so because not every intelligent society should be expected to end up being an intelligent civilization, this is why I'm suggesting that F sub I is not quite 1, but maybe 0.1. It's still a large number, but it's a reasonable number if you would agree. Finally, the longevity of civilizations. How long is an intelligent civilization supposed to last? This is a space station view of Egypt, one of the cradles of civilization on Earth, okay, at night. And, well, they've been around and occupying this place for over 5,000 years, in fact, 5,000 years BC. So at this point, close to 7,000 years or over 7,000 years. But there are things that can destroy civilization historically. Impacts could wipe out life or parts of life. This is the Houghton impact crater on Devon Island. There could be the longevity of a civilization could be threatened by population explosion. So at this point, this is the population on the Earth. We are at about 7 billion people. We're at the end of the blue curve. And the 3 colored curves, red, yellow, and green, are possible outcomes as predicted by the UN. So I'm not sure what, I think green means you use birth control. Yellow means you don't do nothing. And I think red means there are simultaneous power outages in major cities around the world at the same time. Okay, civilization could be destroyed by pandemics. All right, so this is a situation where Cuba Gooding Jr., Kevin Spacey, and Dustin Hoffman are the only survivors. Okay. There could be world wars, all right? So the argument here is that how long can a civilization last? People have proposed 100 years, on average, again, throughout the galaxy to 1 million years, why not? Historically, cultures on Earth have lasted about 500 to 5,000 years. So some say, well, we're now global, we're high-tech, it changes the whole ball game. We should be able to survive for the long run. We're sort of past the hurdle. But the truth is, we are also capable of complete annihilation for the first time. Okay? So it's, in some sense, I'm not sure whether I need to be optimistic or pessimistic. I'm giving us 10,000 years because it just seems like a reasonable number that can be pegged to history. If you want to believe we can survive for 1,000,000 years, fine, but I think it's a bit optimistic. So what numbers do you end up with? Well, this is it. The right column, in spite of us being optimistic somewhat on some numbers, okay, n equals 1. All right? So what this means is that there might be one other civilization out there. If it's at some average distance, it's 50,000 light years away because our galaxy is 100,000 light years across. Okay? So we don't have to worry about Hitler's speeches. They are only 80 light years out. It'll be another 49,000 plus years before they hear Hitler. Or we could be it. I mean, don't get too focused on one. It could be 2, it could be 3. The point here is that we would be really very much alone, okay, pretty much alone. So that, I think, forces us to reflect a little bit. It means that there's nobody out there really that's likely to come to the rescue. We are on our own, most likely. We need to be very responsible. We need to cherish life on Earth. We need to cherish who we are. We may not be the best thing that life can do, but at the same time, we are not doing too bad so far. We've come a long ways. And the good news is that if you're looking out into space again, while we might be alone in our galaxy, there are more than 100 billion galaxies out there. This is the Hubble telescope view of deep space that shows you all these galaxies that are out there. So imagine that every one of them has only one civilization in them. It's still a pretty busy place. Okay? So I think that in the universe, if you include all these galaxies, there must be many intelligences like ours, in fact, more likely farther ahead than we are, since we've just begun to be a civilization 100 years ago. But in our own galaxy, not so much. So where does that leave us? Well, it doesn't mean that there's no life in our galaxy. Okay? There could be intelligent societies with Homo erectus type of intelligences within 10,000 light years. There could be planets with big things that are a bit dumb, but nevertheless very persistent, like dinosaurs, okay, within 1,000 light years. There could be oceans teeming with fish, things like fish, within 100 light years. Okay. There could be planets with plants, forests, simple critters within 10 light years. There could be worlds teeming with microbes within our solar system. Okay, Mars, Europa. So microbes could be fairly common. The odds are that they could be, whereas intelligent societies, much more difficult. I say we should hit the road, and that means go into space instead of fighting ourselves. We've been to the moon. The top view here shows you the Earth-Moon system to scale. And I'm about to wrap up real quick. The Earth is to the left. The moon is that little gray patch that you see there to the far right over there. Okay? This is the Earth-Moon system to scale. The Apollo astronauts went through this entire abyss of space between the Earth and the moon to get there and back. Okay? Ever since the Apollo program, all of our human space flight, including great Chris Hadfield's flight, were within 1 pixel element of the Earth in this picture. Okay? The space station is at 250 kilometers. It's 1 pixel element only. Very local stuff. Going to Mars would be a next quantum leap. I think it's the challenge of our generation. Mars, when it's at its farthest from the Earth, when it's on the other side of the sun from the Earth, is 1,000 times farther than the moon. Okay. Beyond Mars, this is what we can expect in terms of distances. The solar system, of course. Then we get to the point where Voyager is. Voyager is at about 100 astronomical units, so in other words, 100 times the average distance between the sun and the Earth out from the sun. Okay, so it's gotten to this point, the heliopause. Voyager 1, along with Voyager 2, Pioneer 10 and 11 are on their way out, and they're at roughly the similar distances, 100 AU or so. Okay, it's taking them 35 years to cover 100 AU, all right? The time it's going to take them to get to the distance of the nearest star, even though they're not headed that way, Alpha Centauri is 4.3 light years away. It's going to take them 272,000 years to get there. Sorry, it's going to take them 95,000 years to get there. 95,000 years. It's at 272,000 astronomical units. Voyager will take about 2.2 billion years to get to the other side of the galaxy from us. All right, so we need to find a way to travel faster than Voyager, catch up with it. We might be just fundamentally unlucky and doomed. You see here a scene with many galaxies. The big fuzzy one is an elliptical galaxy. It's a primitive galaxy. There's another one that you see on the upper right. There are a few fuzzy ones in the background, but there's a remarkable galaxy right here. This one. This here is a galaxy, okay? It's what you call an ultra-compact dwarf galaxy. It contains 200 million stars like the sun. The star density is unheard of. It's like the highest star density we've ever detected. It's 15,000 times denser than our own galaxy in terms of stars being close to each other. The stars in this galaxy are on average 25 times closer to each other than in our galaxy. Okay? So Alpha Centauri, if we were in that system, would be within the distance of our Oort cloud, just about 10,000 astronomical units out. All right? So it would make interstellar travel a lot easier to be living in that ultra-compact dwarf galaxy. On the other hand, the stars being so close, they would be perturbing their Oort clouds, which are these clouds of comets, okay, surrounding these stars. And so these planets would likely be very heavily bombarded by comets raining in every Tuesday. But interesting possibility. So this is it. That's sort of a superimposed Spitzer view of the ultra-compact dwarf galaxy. All right, so we hope one day, nevertheless, to get to Alpha Centauri. Alpha Centauri has two main stars, which are more or less the size of the sun, Alpha Centauri A and B. B is surrounded by a planet that's about the size of the Earth, a little bit bigger, but very, very close to the star. So close that the rocks are in constant magma, so it's even closer than Mercury from that star. Not a good place to be. But the A and B system at Alpha Centauri is also orbited by a third star called Proxima Centauri. And Proxima Centauri technically is the star that's closest to us right now, okay, because it happens to be on our side of its loop around these two other stars. But that's the nearest star system, 4.2 light years away. And again, if you're traveling only as fast as Voyager, it'll take you about 100,000 years to get there. So we need a better way. Beyond Alpha Centauri, the nearest star is Barnard's star, okay, 5.9 light years away. Barnard's star is a tiny little red dwarf. It's barely bigger than Jupiter. Here it is, moving across the sky over the course of a few years. Now one was done. And then, sure enough, we're still discovering close stars next to us. WISE 1049 5319 is a double red dwarf system. They were discovered essentially, the announcement was just this year. They were discovered over the past 2 years. It's a double red dwarf system that is actually closer to Alpha Centauri than we are to Alpha Centauri. And so all of a sudden, we're no longer the best friends of Alpha Centauri. And to me, it's just remarkable that we can still be discovering stars that close to us. So this is the system, the several shots that led to its discovery, okay, through different infrared imaging systems. So it's been tracking since for a while, and this is a Hubble Space Telescope resolved view of the double red dwarf stars. And then I'll end with this. This is a free-floating planet. This is yet another discovery. This is a planet that is about 6.5 times the size of Jupiter. So it's not a brown dwarf even. It's not even a star. A brown dwarf is sort of the smallest thing that has a tepid nuclear reaction going on. You need to be about 13 times the size of Jupiter to be a brown dwarf. This is halfway there only. This guy is a planet. It's just a bit bigger than Jupiter. And it's not going around any star. It's minding its own business, drifting across the galaxy. It's in Beta Pictoris. It's part of the swarm of stars of Beta Pictoris. Okay, but it's on its own. It's the first time we find a free-floating planet not tied to a star. So I wonder, you have to imagine something the size of Jupiter, in fact 6.5 times the size of Jupiter, okay? So there's no star, so there's no day or night. It's night continually. Being a big Jupiter-type thing, it probably has a strong magnetic field. It's probably aurora. So imagine it's lit by global aurora day and night, so to speak. It's very young. It's only 12 million years old. It's a youngly formed thing, so it's probably still shedding a lot of heat. It might not be inhabited by microbes, but on the other hand, who knows, the upper atmosphere could already be hosting Deinococcus radiodurans and other things that are floating out there maybe. So this is where we need to go. That's the first step. This is the challenge of our generation. Thank you.